Yeah, I think everyone joined, right? So am I audible? And the screen is visible, everyone?
Yes,
Okay. Okay. Good evening, everyone. So how are you all? So all you are undergraduates or working also?
myself, working professional. I think I discussed it yesterday.
Okay. Okay, fine. Okay. So today is a first session and first batch. You're the first batch in Provilogic. So today we are going to discuss on demo, just a overview of the course. So what we are going to learn in the course, in entire curriculum, what are the modules going to be covered, and how we are going to discuss every session and every module, and how the projects we are going to discuss, and what is the outcome when the placements will be started, the tool access. So everything we will discuss today. Okay. And also I will give you the insights of VLSI. First of all, what is the main intention, what you are going to learn now. So in VLSI front end domain, back end domain, in present session now both the PD and DV, both the students are there. Okay. So we are going to discuss mainly that thing. So what are the main insights of VLSI? So if you have any doubts in the middle of the session, so you can ask your doubts. Mostly these sessions are interactive, right? So we will consider only few members per batch, just 15 to 20 members per batch, so that doubt discussions also very good. It will be more interactive, right? So you can no need to hesitate. Whatever the silly doubts also, I can clarify clearly. Okay, so our main importance is for doubt discussion only. That is first priority. Okay, so yeah. Coming to the myself, first of all, what is Provilogic? So what is our vision and mission? So first of all, welcome you all. A warm welcome to one and all. So we are excited to have you with us, and we are stepping into the fascinating realm of VLSA technology, right? So our vision in Provilogic is to make it as a global leader in VLSA training and empowering the students and professionals to excel in the dynamic semiconductor industry. So, and our mission is to deliver high quality sessions that focus on areas where students often lag in meeting industry standards and very at a very affordable budget. So most of the students will suffer with the budget issues, and everyone not able to take the training and all, right? So we want to support from uh, like student level to the professional levels. Okay, so that is our main goal. And coming to the visionary duo behind the Provilogic, these are the founder and co-founder. You already know me, Prashanti Chanda. So I'm going to take care of everything. So technically, non-technically, I'm going to take care. And co-founder Vishwarya, he is also my brother. So the marketing side and the like whatever the programs, new programs, everything he is going to handle. Okay. And coming to my expertise in, I am expertise into the design verification in VLSI design. So till now, I worked with different companies like ASIC and Technologies, AMD. I have worked, and semi design. I have worked from last 4+ years as a trainer, and last position is co-founder and managing director in semi design. So I have worked on various system on chip verification, debugging using RTL design and verification, and proficient in SystemVerilog and UVM methodologies, and also worked on developing various IPs with the industries, and also I have worked with American client in semi design, and worked on complex projects where ASIC designs are involved in various IPs protocols, so SOC design in that way. And I'm also passionate in training. So I'm a dedicated trainer with a passion of mentoring students, and I'm known for patience and understanding. So till now, I have mentored 2000 plus students and good placement report also. So with this work experience and mentor experience, so I thought it is a good thing I can start my own. So we have started Provilogic. Okay, so yeah, that's it. So today, I think I think most of you joined for the first demo session, right? So in the first demo session, we have discussed entire VLSI design flow. What are the technology like the fabrication technology in the transistor wise, how the CMOS technology, FinFET, GAAFET, transistor technology, and the Moore law and nanometer technology. All these things mostly discussed. If you are not able to join that session, I will share you the demo session link. Okay, so you can go through the demo session link. Today's session is on mostly VLSI design flow, how real time we are going to put the knowledge into the VLSI. Okay, so whatever you are learning this 6 months duration of course, how real time we are going to work with the industry. So that thing we are going to discuss today. Okay, and do you have any doubts still here?
Oh,
No? Okay, so if you have any doubts, you can ask me. Uh, Let me see. I need to remember the names also first. Amisha, Deepak, Harshita, Lahari, I know. Madhumita, I know. Naveen, Patan, Piyush, Pranita, okay. Sri Vishnu, Ritesh, Yoganand. Okay. By next 1 or 2, 3 sessions, I will get to know all the names, so I can ask directly. Um, okay, I can call directly. Okay, so coming to the VLSI design flow. So in VLSI, we have front end design and the back end design. Okay, so in the front end design, mostly our focus is designing some chip in a tool and doing the verification. Back end is the manufacturing process. Okay, back end to send the some software data to the back end process. First, we need to verify that, right? Then only we can dump that software into the hardware. Hardware means here we are using the silicon material. Okay, silicon is the hardware material. Into that we are going to dump the uh, whatever we have to blueprint we can call the RTL design. So that RTL design we are going to dump into the silicon. Okay, so while we are doing these things, we need to follow various steps. Okay, there are various steps in VLSI design flow. So you will get to know what are actually. Okay, so front end, coming to the front end design. First of all, suppose there are a lot of processors or chips coming into the market, right? A series in different versions, like any mobile phone. If you consider, suppose you are using some mobile phone, you know the what version you have bought, and what is the previous version of that mobile phone, and what is the latest version of that mobile phone. Okay, suppose the iPhone is there. In iPhone there are generations, 12th generation, 13, 14, 15, 16. 16 is the latest one. So from 12 to 16, what are the major changes are there? Okay, in terms of memory, in terms of storage purpose or camera quality, quality, and the size. Okay, so there are various things, various features will be there in terms of battery. Okay, so first we need to consider the specification. In the specification, I'm just telling the overall, but internally in industry there will be lot of things. Okay, but if we say overall, in specification means what is the present technology and what are the updates we need to put. What are the new features we can add? If any like if something is coming into the market means all the features will not work. Maybe sometimes the features will not uh, get popular, right? So those features may be removed by some next generation. Okay, so like that we need to consider what are the best features and what are the upgrades. Okay, so that thing we will mention in the specification in terms of memory or in terms of battery, in terms of camera or number of cores, how the graphic processor, the technology. So everything will come in the specification. Okay, so specification means just idea of the project. So after specification, architectural design. So architectural design in the sense whatever the specification we are considering, every part we need to design into some like just we can take some pen and paper, just we will draw overall. Suppose in digital electronics we draw the overall diagram like a multiplexer means what, it have n number of inputs to power n inputs, n number of selection line and one output. Like that we will draw some basic structure. Okay, after drawing the structure, architectural design in terms of micro architecture, that will be take care of RTL design engineers. Okay, so RTL design engineers draw the micro architecture of the circuit, and then they write the RTL coding. Okay, so after considering the design, next step is RTL coding. RTL coding in the sense here we have two description languages, hardware description languages. There are Verilog HDL and VHDL. Okay, so mostly industries prefer Verilog HDL compared to VHDL. Why? Because VHDL have some limitations. Limitations in the sense it is somewhat complex compared to Verilog. Okay, in VHDL we need to include some standard libraries, and coding wise also, structure wise also somewhat complex. Okay, so that's why mostly Verilog is preferred. Okay, maybe you may get the doubt, why don't we prefer to design a circuit using a C language or Python or Java? Why don't we prefer these languages? We also have assembly languages. Why don't we prefer in the sense C language or Java, Python, or all these languages are to develop some software purpose. Okay, to develop some application, to develop some websites or some gaming purpose. Those are software, high level languages. Okay, assembly level languages also there to design a processor, to design a course. Okay, what is a processor? Processor is nothing but it have n number of cores, and n number of cores or work with respect to the instructions, right? So if you are studying a BTech, in BTech you will have the subject called microprocessor language. Okay, microprocessor, microcontroller. There we use the assembly language programming, right? Assembly language programming means we will write the program like in this way, like add register 1 comma register 2, and destination register will be there, source registers will be there, subtraction, multiplication, the destination register, source register 1, source register 2, like that instructions will be there. Okay, to design a processor. Why? Because we from childhood onwards we always read like CPU means central processing unit. Central processing unit is a brain of the computer. We'll read like that, right? So what exactly the brain of the computer in the sense how the human brain works. Okay, our human brain will give the instructions to our body, right? So if we want to talk something, the brain will give the instruction to talk, to write something, or to do some work. So everything we will get the instructions from the brain. Like that, in the computer also, in the laptop or mobile phone, whatever, in the computer there will be a processor. Processor is the brain of the computer. That means processor will give the instructions to entire chip. So in chip there are multiple number of blocks like this. I will show you. Like this there will be multiple number of blocks, so to every block this processor will be connected. However, our brain is connected to entire body, every like part, the brain will be connected, right? Same way the processor will be connected in a system on chip to every part. Okay, so That means the processor will provide the instructions. Based on the instructions, every task will be work. Okay, however, our brain provide the instructions to entire body. So those instructions are nothing but these arithmetic and logical instructions which we write in a processor language called assembly language programming. Okay, so like that, to design a processor, we have assembly language. To design some applications, websites, we have some high level languages. Same way, to design the digital circuits. So these all are digital circuit only. Memory, RAM, ROM is a digital circuit, and there will be a counter, special purpose registers. So you know the micro architecture, right? The processor architecture. So processors will be there, counters will be there, final state machines. All these are digital circuits. By using digital circuit, we are going to make some system on chip, some design, right? Some architecture. So to design those digital circuit, we are using the hardware description language called Verilog HDL or VHDL. Okay, so VHDL is not mostly preferred. Verilog HDL is mostly preferred. Okay, so that is what RTL coding. RTL coding, if you see right side, there is a program. It is just a small snippet. Okay, so from the program, after doing the synthesis, here we get the synthesis. Synthesis means from the program we convert the language, the program into the circuit netlist. Okay, by using the tools, we provide the tools, synthesis simulation tools. Okay, so from the code, this is what the circuit netlist. Okay, so that is what RTL design. Once this circuit netlist we got, we need to dump this circuit into the silicon backend process. But can we directly dump into the silicon? No, because we need to do the verification. Because we don't know whether the circuit is generated correctly or not. Maybe there are some, maybe they have some mistakes. It has some mistakes, right? In terms of connection, wire connections, maybe, or in terms of functionality. Okay, it may have some mistakes. So we need to do the verification before sending to the manufacturing process. That's why in front end we have the RTL coding and then verification. When verification is one of the major domain in the VLSI. Okay, so design verification, we always heard like design verification, PD, like that, right? So that is what design verification. Once verification is done, in verification we use SystemVerilog and UVM languages. Okay, so once verification is done, we will check if everything is correct, then we can go to the backend. If something, if any functionality mistakes are there, if any connection mistakes are there, again we send to the RTL code and recheck. Okay, next, coming to the physical design flow. Physical design flow is the backend process. Okay, so in the backend process, before physical design, there is a logic synthesis and a DFT. If you see here, before backend process, there is a logic synthesis and DFT. Logic synthesis is nothing but gate level netlist. Like however we get the circuit diagram here, we will check every gate to gate connections, whether it is working properly or not in a synthesis step. That is a gate level correction. Okay, uh, logic equivalence checker, that will be done in the logic design. After that, physical design. Physical design means PD. That is the main major role, major domain in the VLSI. Okay. So physical design means here we follow some flow, like steps. Okay. So first one is a floor plan. Floor plan in the sense, suppose here we got the circuit diagram, right? So after getting the circuit diagram, there is a silicon material. How the silicon material will be taken? Will cut into the wafers, very small thin wafers. Okay, suppose this is what the silicon wafer. In the silicon wafer, whatever the circuit is, that circuit we need to dump into the wafer. Okay, so the circuit structure, exactly, if you see, the structure will look like this. This is what system on chip circuit. Okay, it consists of processor, different memories, and like there will be IO peripherals like Wi-Fi module, GSM module, Bluetooth, and display unit. The peripherals will be there, like protocols will be there. These orange color are the bus connections. That means one block to another block, we connect the bus. Okay. So like this, we get the circuit diagram. So that circuit diagram, the RTL design engineers will generate. That one we need to dump into the silicon wafer. Okay, so to dump into the silicon wafer, we need to check, right, which block will get at which place. Suppose if you see the olden motherboards, on PCB, there will be lot of circuits. Processor will be there. Upon processor, there will be a fan. If you see right side, there will be big slots, PCIe slots, and there will be some bridges, north bridge, south bridge. Like that, the structure will look like that, right? So same way, so we need to check where we need to put which block should place. Okay. So based on that, what is the size of each block, and we need to check, same like a house construction. I already told this example. So how we build a house? First, in a front end, we go to some engineer plan, we go to some engineer and we get the plan, house plan. So same house plan we will do the construction, right? In the house plan, according to some vastu or anything, we will take a correct size. I mean, where the bedroom should put and where the kitchen hall, so everything where we should put, and sizes, like what are the width and the depth, particularly we will check everything, right? In the same way, however we put everything in a same order, particularly here also we need to follow what is the each block size and where we need to put. Okay, so that is what here we get the lot of steps like a floor plan. Before thing is the floor plan, like in house construction we do basement first, like that here we do the placement, I mean floor plan. After floor plan we place all the blocks like this. So that is what placement we have for. We need to follow a lot of steps, that is different. So that is what placement. So after placement, clock tree analysis. Clock tree analysis, in the sense, in the house construction we connect some power, right, which with each rooms and all, there will be a power connection. Same here, we have the power connections. Clock tree analysis, like that, same physical design comes in the back end, and these are the steps. See, floor plan, placement, clock tree synthesis, routing. Routing, in the sense, we connect everything, wire connections between all the circuits. Static timing analysis. Static timing analysis, we have front end. We will discuss front end domain and also back end domain. Okay, so here we will discuss mostly the stucket faults and the setup and hold time analysis, because in the flip flop majorly we'll check, we'll get the issues with the clock. Okay, so the setup time is properly connected or not, the hold time analysis is proper or not, we need to check in the static timing analysis. After that, physical design, physical verification and sign off. Anyway, every step we have the testing. Without testing we don't go to the next step. Okay, after floor plan, we need to do the testing. After placement we need to do the testing. After routing we need to do the testing. So testing is common for every step. Okay, and finally physical verification, overall verification, and then tape out. Tape out, in the sense that the manufacturing process is done. Okay, so this is what the front end VLSI domain and the back end VLSI domain. Is it clear, everyone, till here?
Yes, ma'am.
Any doubts? Tranisa, any doubts?
No, ma'am, no.
So if you have any doubts, let me know.
Actually,
Okay.
Yeah, sure.
Yeah.
am I audible?
Yeah, please tell.
To the before slide.
Before
First
slide.
RTL
Okay.
design. Yeah. Yeah, RTL coding. Next we'll go for functional verification. Am I audible?
Yes.
RTL coding, yeah, generally we go for the Verilog. Yeah. But now here functional verification is done using SystemVerilog or UVM. So this is a methodology we are using to verify the Verilog return code. Is it?
Yes.
Okay. So code will be in Verilog itself, which functional verification is done, and then we'll be going for the next backend flow with the
Mm.
Verilog code itself. But functional verification itself is done using the system Verilog on UVM. This is a
Yes.
one step. That's it.
Yes, sir.
Okay. Right.
SystemVerilog
That's
is a language. UVM is a
it.
methodology. Why we are calling it as a
Oh,
methodology means, suppose SystemVerilog, like a Verilog, suppose. In UVM,
mhm.
everything is a predefined libraries. Suppose in SystemVerilog, everything we need to develop from scratch. If you want to write some program, we need to develop everything from scratch onwards, the functionality, everything. But in UVM, everything is a predefined. We can call the parent class and we can access all the things from the libraries. Okay, so that's why we call it as a methodology. And also it takes
Okay.
less time to do the verification using UVM. By using system verilog it takes some more time. By using verilog it is more complex to do the verification. That's why verilog is not preferred. System verilog and UVM is mostly preferred.
You mean to say like UVM from system Verilog, but it
No,
has a no.
UVM is from system verilog, yes.
Yeah, from system Verilog, and it has a like test cases. Every environment will be built
Thing is
using this concept. Everything is
same.
there, but the concept will be using from system Verilog. You mean to say?
Yeah, yes. Concept wise, similar to system Verilog, but UVM have some more features, advanced
Oh,
features. Yeah.
okay.
Okay, so that is what front end domain and the back end domain. We have another domain in VLSI, digital VLSI called DFT, designed for testability. This is also comes before physical design. That means after doing synthesis, here we insert the DFT. That means we insert some ATPG technology, the scan insertion, just to check whether each um, in the after synthesis whether the circuit is working properly or not. It just by using the scan methodologies we will check the pattern simulation, everything, the circuit faults, whether design is working properly or not. So that is design insertion. In PD we are going to discuss the DFT also, just insights of DFT we are going to give. Okay, so what is scan chain insertions, ATPG technology, pattern simulation? This is for PD engineers. Okay, so this is entire flow, ASIC design flow. First is a specification. Then from the specification, we need to draw the architectural design. That means overall understanding of a problem statement. Suppose any problem statement is given in digital electronics. What is the problem statement? Suppose there are 4-bit input. 4-bit input means four inputs. Suppose there are 4 inputs. 4 input means how many combinations will get? How many scenarios we can expect for 4 input variables?
16.
16. 2 power 4, 16 combinations will get, right? So a problem statement is given. There are 4 variables, A, B, C, D. There are 4 variables. In the 4 variables, whenever like 0 0 0 0 like that, 16 0 0 to all ones. Okay, so if there are even number of ones in the combination, output should be 1. If there are odd number of ones, output should be 0. This is what the problem statement. Okay, so for this problem statement, if any problem statement is given like this, we need to understand the functionality and we draw the diagram. What are the number of inputs? Like 4 inputs. How many outputs? Like 1 output in this problem statement. If any control signals are there, control signals means clock, reset, or any other signals. Okay, we need to mention. This is what overall block diagram for this problem statement, right? In the same way, here specification. Specification means just a problem statement. Architectural design. That means drawing a block diagram. for the design, and RTL design, writing the program, Verilog program to design in a tool. You may get the doubt that directly we can design manually, right? Then why we are using the program and tool? In the same, why we are using means for simple circuit we can design manually, but nowadays we are using billions of transistors in a single chip. That means lakhs of gates, lakhs of blocks, billions of blocks we are using in a circuit, right? We cannot generate that manually. That's why we are taking the help of tools and the programming language, hardware description language. Okay. And then logic synthesis, DFT, and backend process, floor plan placement, CTS, routing, all these all in the backend process. Okay. So next, so how many of you know the difference between ASIC chip and FPGA? What is the difference between ASIC and FPGA? So ASIC chip is the application specific integrated circuit. Before we have seen all these steps, right? From architecture design to the backend process. So after doing all the process, what is the final result? This is the final result. Okay, the chips will be manufactured like this, right? So to design a ASIC chip, we need to follow entire flow. Okay, so ASIC means application specific integrated circuit. That's why we call it as a ASIC design flow. Okay, it's a permanent chip. Permanent chip means what? Whatever we are whatever the functionality is there here, that functionality is taken from the specification itself. Okay, so from the specification only we are designing that structure. From the structure we are doing entire these things. Okay, so it's a permanent chip. Once it is done, we cannot change, we cannot reprogram. Okay, so according to the application we are designing that particular chip. According to the laptop version, we have separate processors. According to the mobile phone, we have separate processor. In ATM machine, if you see, there will be a small chip when you are inserting the ATM. uh, there will be a small processor, right? Small chip, gold color. Even that is also a chip. Like that, every digital gadget have some chips. They are designed they according to their own functionality. Okay, so once if they are damaged, we cannot reprogram it again and again. We just need to throw. Okay, so that's why we call these as a ASIC chips, which are permanent chips. The processor, whatever we are using in our laptop, mobile phones, all these are permanent chips. And coming to the FPGA, FPGAs are temporary. Like we can reprogram it again and again, like a boards. If you see like IoT projects, you may work with IoT projects like embedded system projects like Raspberry Pi or some Arduino boards. So whatever the program we need to do, whatever the project we want to do, we dump the program and we check the output. We use the board for that functionality. Again, for another project, we can reprogram the board and we can use for another project. Okay, same for VLSA projects. If you want to do something with the board, then you can choose the field programmable gate array, FPGA, which is a reprogrammable, same as a ASIC chip, but it is not a permanent chip. We can reprogram n number of times. For projects mostly we use. Okay, we dump the program, we use, and we can reuse. That's it. These are like a older versions. FPGAs or anytime these are popular because every time we use FPGA chips. But nowadays, compared to ASIC chips, we are using system on chip design. Okay, system on chip designs are most of the laptops or mobile phones everywhere we use SoC design nowadays. That means if you observe the olden computers, there will be a CPU, box type CPU. In that, you will find some motherboard. In the motherboard, we will place everything separately. So if you see how the motherboard size, So here we insert the processor. There is a like a south bridge IO, north bridge IO, and these white colors or PCI slot. That means everything we buy separately. The components, every component we buy separately, even ports, all these, everything we buy separately and we insert on a PCB port. Okay, but nowadays system on chip design means we doesn't consider all those boards. It is just a chip. On the chip we will place everything, the circuits. If you see the blue color here, right side, it is a chip like a wafer, silicon wafer. On that we will place every small component directly. Okay, we don't buy any separate component and we don't place. Okay, so like this everything is integrated on a single chip by default at the manufacturing time. Okay, so these are the structure. This is a basic common structure where it represents a processor. Inside the processor there will be n number of cores. Cores are nothing but every time if you buy some laptop or mobile phone we will check the core, right? What is meant by core? What is meant by a core? Suppose you may see in your laptop like there are 4 number of cores, 8 number of cores. Why are you not answering? Rahman, what is mean by core?
Ma'am, it can be a CPU core and it can be in multiple cores.
Yeah, what is the difference if we have more number of cores? What is the benefit? Or if there are less number of cores, so what are the limitations?
If there are more number of cores, then the processing speed will increase.
Okay, okay, good. So more number of cores means suppose there is a single core. Single core will do 2 number of tasks. Like 4 number of cores will do 8 number of tasks. 8 number of cores will do 16 number of tasks. Okay, so whenever the number of cores increasing, the speed, the processor speed, that means it is doing multiple tasks at a time, right? It able to do multiple tasks. So automatically processor speed will increase. Okay, so that's why we always check how many number of cores are there. If there are more number of cores means it is a high level chips. Okay, so that is the core where the processor will work with respect to the instructions, assembly language, program, everything. And here there are different machine learning related subsystems and memory subsystems, some peripheral subsystems. These are as of now not required. We will discuss in the coming sessions, in coming days. Okay, so that is what system on chip. All these blocks are Verilog HDL. We design using a Verilog HDL. All these are RTL design, but except the processor. Processor is not designing with a RTL code, right? It is designing with a assembly language program. Okay, so that's why to verify the processor, we use a C language or C++. We cannot verify the processor using SystemVerilog. Why? Because SystemVerilog or UVM use it to verify a hardware description language, Verilog or VHDL. Okay, so that's why entire SOC we do verification using SVUVM for RTL design, except a processor. For processor, we use a C or C++. Okay, so that's why if you see, if you go to industry, there you will understand. In SOC level, we never use SVUVM just to verify the processor. Okay, so yeah, any doubts still here?
No, ma'am.
No? Okay. So first we will go with our main course module. So what we are going to learn in this 6 months duration, 5 to mostly 6 months, not 5 months. We cannot complete in 5 months, mostly 6, 7 months like that. So ASIC design verification. Coming to the course curriculum, In this, we are going to cover 6 modules. First, digital electronics, then Verilog HDL, and then SystemVerilog, and then UVM for verification, and then Perl scripting and design verification projects. Okay, so here advanced before that demo session is on overview of VLSI design. We already discussed today. Front end versus back end discussed today, and industry requirements we will discuss in the coming sessions. ASIC chip, FPGA, SoC discussed today. Moorla nanometer last session we discussed. I will share you the recorded session of that. I think most of you attended. And importance of digital electronics and introduction to RTL design and verification. So importance of digital electronics means whatever the chip I have shown before, the system on chip. So in that everything consists of a digital circuit only. Whatever the memories or finite state machine, register, counter, or arithmetic logical unit or any multiplexer, all these are digital circuits. So those are not a basic level. Whatever you learn in a graduation level, even I think you don't remember what is a truth table, what is a excitation table, what is a how to design the circuit. That is a very different. But industry requirement is very advanced level. Okay, so we need to learn everything in terms of industry requirement. We need to meet their expectations, right? So that's why we are going to cover advanced digital electronics. Okay, so mostly how the interview questions will be asked for every topic, like multiplexer is there, how we can design a various models of multiplexer, a counter design, how we can simplify the counter logic, the register logic. Okay, so that thing we are going to learn, and RTL design and verification. So first module 1 is the advanced digital logic circuit. Okay, what is the schedule means? For first 1 week, I will share you the material. Okay, document like a PDF from our Provilogic. So first you need to learn all the concepts. It's a revision. Okay, I'm not going to teach everything for the digital electronics. I'm not teaching from scratch onwards because already you know, just revision is enough. Okay, so once you revise what is mean by logic gate, what is mean by Boolean algebra, combinational, sequential, register, counter, you will get overall idea because already you learned. Okay, so after that, from second week onwards, there will be regular sessions. In first week also I will take the session, 1 or 2 sessions. Okay, from second week onwards there will be a regular session, alternate days. Okay, our sessions not daily, alternate days. One day is a live session, next day is for assignment practice, and then live session, then assignment practice, like that, alternate days. Even if we discuss daily also, you won't get time to practice. Okay, that's why alternate days live session, alternate days assignment practice. Okay, so from second week, in second week we will cover all basic topics of interview questions, interview point of view. And third week, all combinational, sequential interview point of view. And fourth week also mostly shift registers, counters, FSM, memory. All these things will be covered. Static timing, CMOS also covered parallelly. Okay, so mostly within 1 month we will complete the digital electronics. Okay, so it totally depends on you. If you complete fast, we will complete our sessions quickly. If you take lot of time to submit the assignments, it will take delay. Anyway, I will give you lot of time to practice, but if you work with time, that will be good for all. Okay, so that is what our schedule for digital logic design. Mostly 3 to 4 weeks we work on digital electronics. Advanced only, not basics. So also we are going to cover these glitches, hazards, interview preparation, regular assignments will be there. And second module is Verilog HDL. From Verilog HDL, we are going to discuss everything from a scratch onwards. Okay, from scratch means everything we will start with the data types, applications, operators, and then next week how to model the circuits using Verilog HDL in different models like a behavioral, data flow, gate level, switch level. Parallelly, we will cover the lab sessions also. Okay, so lab sessions separately, theory is separately, not like that. Parallelly, if we discuss one example in theory, immediately we do the lab session. Like that, we will cover all combinational circuits, sequential circuits, and finite state machines, registers, counters, everything we will design using Verilog HDL. Okay, and there will be lot of topics also, like blocking assignment, non-blocking assignment. So both theory and lab sessions will be covered same like this only. So next, all these memories also we are going to discuss advanced memories like a FIFO memory. Actually FIFO memory is like a minor project. Okay, but here we are covering like a normal topic. Okay, not like a project. You can mention as a project also in your resume. You can mention as a project, but I am not including it like a project. I'm just giving like a normal memory session. Okay, so RAM, ROM, and test bench concepts are very important. So we are going to discuss all from basic to advanced. Okay, and then after Verilog HDL, we are going to discuss System Verilog. System Verilog also same. We are going to start from basic onwards. There will be regular live sessions, regular assignments. Every concept we are going to discuss. We don't skip any concept. Okay, because every concept is important. Even it is a small concept, it have huge demand while developing the test bench. Okay, so that's why we don't miss any concept. We will discuss from data types, structures, arrays, architecture, queues, memories, interfaces, clocking blocks, everything. Okay, everything discussion in the sense we cannot see one thing. My main aim is to give proper idea, proper knowledge on in real time. Okay, suppose object oriented program is there. No, we do not cover like a definition. We need to cover everything in a real time. Like you need to visualize the concept in a real time, how we can apply the some concept into the project. That is very important. Okay, nowadays most of the students are learning, but they don't know how to apply the same concept in a project level. Okay, how to apply the polymorphism concept in a project, how real time the polymorphism is working in SOC level, how inheritance work in SOC level. No one is not getting proper idea. Okay, but we need to learn very clearly. Okay, so I can give best examples from my side, but from your side also I need very good support, because the play coming to the placements time, if you don't put your efforts properly, there is no use of giving 6 months of training for you, right? So that's why from day one onwards I'm telling, follow strictly. Okay, by end of the sixth month, from at the placement time, everyone need to crack the interview properly. Okay, so that is the my main aim. So I'm going to get the best placements, and I'm requesting to all. Okay, so you need to like we need to prove ourselves. Okay, in a Provi logic. So that's why try to learn every concept clearly. Whatever the doubts you get, and whatever the assignments we are providing, try to build your like what we say, try to learn clearly the concept wise. Okay, so whenever you are facing the interview, you should be topper of that interview. Suppose if there are four numbers in same line, you must be selected. Okay, we need to learn in that way. Okay, that's why from day one onwards we need to put our efforts. Okay, so we need to show the differentiation, how the how the course content in the Provi logic, and how we are going to learn the things. Okay, so I need to build a good network. Okay, I want to build a good student, very knowledgeable, which we can use some for the industries. Okay, so that's why quality of engineers I want to give to the industry. That is the my main aim. So for that, if I want to achieve that, your support, your learning is very important. Okay, so that's why. So whatever we discuss, try to form a group, make a interaction with your group members, okay, and try to discuss your doubts regularly. I will post regularly some important questions, everything. So try to discuss yourself, okay. So like, however, in offline, in online also try to discuss in the same way, okay. I will be available for the doubts at any time. You can ask in the session, you can post in the group. If you have some urgent, serious doubts, you can call to me and you can ask. Okay. I will assign you some other mentors also. You can ask to some mentors if I'm busy. Okay. So that's why I'm expecting a lot from you because I'm going to train the best, right? So you need to crack the interview properly. That is my expectation. So we need to show the difference. So then we will get more placement opportunity for next batches also. If you perform good, because this is the first batch. If you perform properly, we will get best opportunities for next batches also. Okay. So we are going to cover the code coverage. Coverage is a very important concept in verification. Coverage, assertion based verification, whoops, these all are very important. So everything we will discuss in terms of programming only, not just a basics. Okay. So how to develop the test components, test plans, test cases. So there will be both lab and theory and assignments. And coming to the UVM, once a system verilog will take mostly 1 to 1.5 months. Okay. And then UVM we will learn starting with the SOC IP level, how we do in SOC IP level, and basic converts from basic to advanced level. Introduction to UVM, test bench hierarchy, sequence items, phases, all the concepts in theory and labs. Okay. So RAL models, everything. So even if I explain now, you may not understand the concept. Next, scripting language. We are going to cover the scripting language, like Linux setup and Perl scripting, how to run the commands and coverage report extraction, how to run the regressions in SOC level, how to debug the test cases. That is very important thing for the verification engineers. Okay. And projects and protocols are very important. Our main thing is the projects and protocols only. Okay. So we are going to cover 5 industry protocols, UART, I2C. So you can go to the schedule afterwards. UART, I2C, AMBA protocol, APB, HB, XI. For freshers, these are very high demand protocols. Okay. We are going to implement in a SVUVM. Okay. And then projects also, we have a best projects: router project, DMA controller, RISC-V processor project, 4-port calculator, DDR memory, PCIe for experienced engineers, USB, Ethernet. You can select any 3 projects. You can work n number of projects. I don't have any restrictions. If you want to work on more number of projects, I can provide some extra mentor. Okay, that totally depends on your uh, your interest. Okay. So if you are interested to work on more project, if you want to develop your wish, I can provide you n number of projects. Okay. With the entire guidance, we will provide you 3 projects. Okay. And so that is what design verification structure. The course curriculum will be there, and structure wise, and tool access. There will be mock interviews, resume guide, and live sessions, mentorship, and placement. So this is what design verification. Is there any doubts? In design verification, we have levels like graduated, for professional growth, and for who are doing masters. For undergraduate students and fresh graduates, no need to learn very depth. If you are interested, I can, but no need to learn very depth of UVM, writing the test cases, that are not required. For professional growth, we will provide advanced UVM and advanced system verilog. So where we can develop a lot of test benches, test cases. That is very important. And for masters who are doing MTech or abroad, who are studying in abroad, master students, we have a global courses like where we provide both the training plus internship. In internship, you will get extra projects like SOC based projects. Okay, so that is what the schedule. And do you have any doubts still here?
How about the lab sessions?
Lab sessions for design verification, we are not going to provide the license. License is not required for design verification because we have a lot of tools, free tools. For PD, we provide the license tools. Okay. In design verification, tool knowledge is not so important. Why? Because our main is writing some coding. Coding is a main thing. In interview also, no one asked on which tool you used. Okay, in which tool you have programmed. They will ask how to write the program, how logically you can build some program. Uh, Test cases, how to write the test case, how to write the test plan. Those are very important. So our focus is mainly on that. Okay, for DV. And DV, we have best tools. Okay. Uh, and for physical design, we use the Cadence license tools. Okay. So in PD, normally if you see outside any other like any other cohort, they will just provide only PD. But here in ProviLogic, we are giving RTL design plus physical design because we need to meet the industry requirements, right? So nowadays industry expectations are very high. Okay, so competition is very high even for freshers or experienced engineers. So first we are covering with RTL design first 1 month, and then physical design flow and Linux scripting will be there, TCL tickle, um, and then RTL to GDS flow, DFT insertion. We are discussing both. Okay, DFT is also, I just want to give overview. Okay, um, and then minor projects and major projects in PD. So RTL design is same. Physical design, before we have seen, right, floor plan, power planning, placement, clock tree analysis. So everything we need to learn in detailed. So that is what PD, and so everything I have given properly. Overview of PD, in floor plan and power plan what we are going to discuss, and placement, clock tree analysis, and routing, timing and signal integrity, power analysis. For PD also we have best trainers. We have 10+ year experienced trainers who are working in product based companies. So uh, those are going to train, okay, for PD. And scripting, RTL2, GDS projects and protocols. So these are the major projects in physical design. Okay. Any doubts still here? From today is Wednesday, right? So from Friday on, already batch has started for design verification. I will share you the assignments and what to learn. Okay. So I will tell you in the group and in the next session how to start and for digital electronics. Okay. So yeah. Any doubts still here?
How about this advanced verification codes? Which has like advanced system Verilog, advanced UAM.
Advanced
So that
verification course means it is from SystemVerilog. UVM scripting project protocols, not the digital electronics Verilog HDL. If anyone know digital electronics Verilog HDL, they can start with the advanced verification.
Yep. From when that it will start? Like from February or
Advanced verification from February. Demo session, yeah, I can share the demo session. You can ping me in the WhatsApp, or else you can go to the Provilogic YouTube. Only one session uploaded. That is a demo session. Okay. Any doubts, Pranita, Rahman?
No doubts, ma'am. Thank you.
Okay. Okay then. If you have no doubts, we can fees. Fees 50,000 for design verification. Okay. Which course will suggest for final year students? If you are BTech graduate, you can take a job oriented course. If you are MTech, MTech have some more expectations, right? You can go for master's course, master's DV. Okay. Any other doubts?
advanced verification course. What's the cost?
Yeah, advanced verification course means in that we have SystemVerilog, UVM, scripting, and projects protocols. In advanced verification, digital electronics and Verilog is not included. If you already know design, then you can take a verification part.
Yep. What is the
Yeah.
cost of this?
Let me show advanced verification brochure also. In advanced verification, we included SOC level also, SOC level things, which is not included in job oriented. I mean, ASIC design. So these are first one, revision on RTL design, module 1. Second module, SystemVerilog for verification. Third module, UVM. Fourth, scripting. Fifth, verification projects and protocols. Sixth is a system on chip design, extra one module. System on chip design in the sense, so in SOC verification, how we do and IP verification and what are the verification approaches, pre-silicon and post-silicon verification. What is the difference between verification and validation, and how we can debug the test cases in SVUVM, like a debugging techniques, and some block level, SOC level implementation. So there will be a SOC design. To that SOC design, we need to write the RTL program and also verification. So this one included in the advanced verification.
Okay. What is the cost of this advanced verification, and is the placement guidance and that is included in that also?
Advanced verification is a 35,000. Job oriented course is 50,000. With placements.
Ma'am, should I join job verification course if I am in my 5th semester?
See, you are in which semester? Fifth, right?
Fifth.
From fourth semester onwards, you can start VLSI. Like you can start working on VLSI from fourth semester onwards. If you start
So,
early, by third year, final year, you will get good internships. You can apply for the good internships, stipend based internships in product based companies like that. If you start early, if you start from final year, you're just eligible for job only. That too, it will be delayed after final year means. Fifth semester is best time to start.
so it would be better if I join design verification course.
It depends on your interest. I don't suggest to join particularly in design verification, because if you are interested in PD, you can choose PD also. But DV is a good, easy to learn, and a lot of job opportunities. DV is also good.
So I should not enroll currently in this course, design verification course.
You want to enroll or not?
So I'm interested in it, kind of.
Okay. Okay. So if you
But
are interested, you can ping me. Yeah, please tell.
but I'm not sure